This is the third video lecture for section 2.7 on apportionment. In this lecture, I'll be talking about something called the Standard Divisor. So the basic apportionment problem goes like this. We have seats in a legislature, and we want to assign them based on population. The natural way to think about doing this is to say, okay, what percent of the total population does each state have? And then we apply that same percentage to the total number of seats. We call that percentage of the seats each state's fair share. But the problem is that those fair shares are typically not whole numbers. Now, because those fair shares aren't whole numbers, we think we would either want to round them up or round them down. If we round the fair share up, that's called the state's upper quota. If we round the fair share down, that's called the state's lower quota. And the quota rule says that we should assign to each state one of those two numbers. We should either round for each state, round their fair share up, or round it down. And last time we learned Hamilton's method, which is a specific way of figuring out which states get their upper quota and which states get their lower quota. The problem is, as we saw in the previous video, the problem is that Hamilton's method suffers from some strange paradoxes. So we're looking for a different way to do this. Now, Jefferson's method, named after the second president of the United States, is going back to the original idea of rounding down the fair shares, right? If you remember how Hamilton's method worked, the first step was to take all those fair shares and round them all down. But the trick is to round down all those fair shares and not have any leftover seats. Hamilton's method was all about how to assign the leftover seats that we got when we rounded down. With Jefferson's method, we want to sort of cleverly round everything down and yet still have the exact right amount of seats. And this involves using something called the Standard Divisor. So in this example, we have a country with 4 states, and the total population is 300,000, and let's say that we have a legislature with 50 seats. So each individual seat represents 1/50th of the total population. Or in other words, if we take the total population here being 300,000, I'm getting that from here on my chart, and then divided by the number of seats, that gives me 6,000 people. And this means that each seat represents 6,000 people. So the standard divisor, we've got a little formula here. The standard divisor is the total population of the whole country, not just of an individual state, but the total population of the entire country, divided by the number of seats. So when we do that, that tells us how many people are represented by each seat. So instead of using percentages like we did with Hamilton's method, we can use the standard divisor to figure out the fair share for each state. So what we're going to do is we're going to look at state A here, and we say, okay, this is the number of people in state A, 87,438. So how many groups of 6,000 people live in that state? In other words, how many representatives should that state get? So the fair share here is going to be the state population divided by that standard divisor. So this is going to be 87,438 divided by 6,000. Remember, on the previous slide, we figured out that the standard divisor was 6,000. So on my calculator, I'm typing in 87438 divided by 6,000, and that's going to give me 14.57. And then going to do the same thing for B, C, and D. So I'm going to take B's population, 82,511, divide that by 6,000. I get 13.75. Take C's population, 66,942, and divide that by 6,000. That's going to give me 11.15. And then 63,109 divided by 6,000 is going to give me 10.51. And if I add up all those fair shares, I'm going to get pretty close to 50. I was cutting off some of the decimal places there, so it might not add up exactly to 50, but it should be very close to 50. Now, those fair shares are the same fair shares we would have gotten if we had done this using percentages like we did in the previous lecture. So it's the same numbers, we're just getting them in a different way. We're getting them using the standard divisor. And then again, if we were going to round down all these fair shares to get the lower quotas, that just means chopping off the decimal places. So we'd get 14, 13, 11, and 10. And then the problem is the same problem that we came up with in the previous lecture, that that's only 48 seats. And we're supposed to assign 50 seats in our legislature, so we have 2 excess seats, 2 seats left over. So Jefferson's idea says, okay, the way to fix that is to change the divisor, right? Instead of dividing those populations of those states by 6,000, we're going to divide them by a different number. We're going to have to make that divisor a little bit smaller. That'll make the fair shares a little bit bigger, And if we pick the right divisor, then when we figure out those slightly larger fair shares and round them all down, maybe those numbers will add up to 50. Now, of course, that doesn't tell us what number to divide by, so we have to use a little bit of trial and error. So we know we need to make the divisor a little smaller, so that will make the fair shares a little bit bigger. So we're just guessing here, but let's take the number 5850. That's a little bit less than 6,000. Let's see what happens. So again, for these fair shares, what I'm doing is I'm taking the state population and dividing it by the divisor. Now, it's not the standard divisor anymore. It's a different divisor because the standard divisor was 6,000, so this will be some smaller number. So in this case, this will be 87,438 divided by 5850, and let's see what that works out to be. So again, I'm grabbing my calculator, 87,438 divided by 5850. That works out to be 14.94. Next state, 82511 divided by 5850 is going to be 14.10. 66942 divided by 5850 works out to be 11.44. And then 63109 divided by 5850 works out to be 10.78. Okay, now if I add up these new fair shares, they will not add up to 50. Right? Because all of those numbers are a little bit bigger than they were before, because I divided by a smaller number, and when I divide by a smaller number, I get a bigger answer. But what's important now is what I'm hoping will happen is that when I round these fair shares down, when I go to the lower quota, chop off those decimal points, now I'm hoping that these rounded numbers, these whole numbers, will add up to 50. Now, I ended up being better, right? So it's 49, which is closer to what I want, but not close enough. So I need to make the divisor smaller still, right? So going from 6,000 down to 5850 helped. Now I only have one excess seat, but it didn't help enough. So I need to make the divisor even smaller. So let's try again. This time we're going to use 5,700. But again, it's going to be the same basic idea to figure out these fair shares. The state population divided by the divisor, right? That's why we call it a divisor, because it's the thing we're dividing by. So again, for that first state A, it's going to be 87,438, this time divided by 5,700. And again, I'm grabbing my calculator. 87438 divided by 5700 is going to be 15.34. And I'm going to do the rest of the states the same way. So here's how those work out. So again, I don't really care what these new fair shares add up to, right? That's not really relevant to me. What I'm hoping is that when I round all these numbers down, that those numbers will add up to 50. So I'm keeping my fingers crossed. So I get 15, 14, 11, and 11. And unfortunately, now those add up to 51. So we went too far, right? Remember in the previous slide, our divisor wasn't small enough, so we needed to make it even smaller to bump up the fair shares even more, but now we went too far. So unfortunately, this is really how Jefferson's process is going to work. We're just going to keep trial and erroring until we stumble on a number that is the right number. So, but let's think about which way we want to go. We don't want to make the divisor even smaller, because then that would make the fair shares even bigger, and potentially this sum of my lower quotas would be even higher. It's already too high. That means I need to bump the divisor back up to make the fair shares a little bit smaller, not too small, but a little bit smaller, so that those lower quotas add up to 50. So we know that 5850 was too big, 5700 was too small, so we're going to do a Goldilocks kind of thing. We're like, all right, we're trying to find the number that's just right. So we know it needs to be a little bit bigger than 5700. We know it needs to be smaller than 5850, so we're just going to make an educated guess. Let's try 5800. That's in between those two numbers that we tried. And again, we're going to do the same type of calculation. So for this fair share, we're going to take the state's population and divide it by the divisor that we're using. So third time's the charm here, we hope. So we got 87,438 divided by 5,800. Again, grabbing my calculator. Definitely can't do these ones without a calculator. So 87,438 divided by 5800 works out to be 15.07. And then again, I'm going to do the rest of these the same way. And here's how that works out. Again, we don't really care what these fair shares add up to, but we're going to round all of them down. So the lower quota here is 15. 14.22, chop off the decimals, we get 14. 11.54 rounds down to 11, and 10.88 rounds down to 10. And finally, we got our result. So that adds up to 50. That's what we want. So this is our apportionment from Jefferson's method. A gets 15 seats, B gets 14 seats, C gets 11 seats, and D gets 10 seats. So it can be a little time consuming. You have to trial and error a few times. You might be a really good guesser and just guess correctly the very first time, but usually you have to try at least a few times until you stumble on the right number. Now, one of the advantages of Jefferson's method is that it doesn't suffer from any of those weird paradoxes that we talked about with Hamilton's method. However, Jefferson's method can result in quota rule violations. Remember that the quota rule says that your original fair share using the standard divisor, the same fair shares we were talking about with Hamilton's method, you should either get for each state that number rounded up or that number rounded down. So let's think about this example. So we've got this example with 4 states, E, F, G, and H. And if you want to work on this on your own, you can pause the video, but use the same method we just did before to apportion 50 seats among those states. I'm going to show you the answer on the next slide, but if you want to try it yourself, give it a shot. Okay, so we start by looking at the standard divisor. So where is this number 4411 coming from? Well, what I did is I added up the populations of all the states to get the totals, divided that number by the number of seats. So this 4411, that's the standard divisor. And that is the total population of the entire country divided by the number of seats. And when you work that out, you get 4411. And then to get these fair shares, where are these numbers coming from? This is the state's population divided by that standard divisor. And then the lower quotas are all of those numbers rounded down. And so as we typically see, we say, hey, 48, that's too small. We've got 2 extra seats, so we need to make our divisor smaller. And so in this case, a correct answer, there's more than one correct way to find a divisor that works for Jefferson's method, but a correct answer here would be 4,200 people. So these numbers are all the same. I didn't change the populations of any states. These numbers here are the state's population divided by this new divisor. So in this case, divided by 4,200. And then again, I rounded them all down to get my lower quotas. They all added up to 50, which is what we want. But now what I want you to see here is that for state E, so state E's fair share is 21.98. I covered it up there with my ink. There we go, 21.98. So the lower quota for E is 21, as we see here. The upper quota for E is 22. If we rounded that number up, we would get 22. So the quota rule says that no matter what method you use, state E should either get 21 seats or 22 seats. But unfortunately, Jefferson's method assigned state E 23 seats. So does that mean that this is garbage and we should throw it away? No, it just means that this violates a different way of measuring whether this is a good method for finding how to apportion our seats, right? So this is just kind of like our fairness conditions earlier in the course. It's just a way of measuring that this might not be the perfect method. So there are other alternatives, other variations of Jefferson's method. Adams's method, developed by our 6th US president, says that we round all the fair shares up instead of rounding down. So rather than starting out looking at the lower quotas and then tinkering with the divisor to try to make them all add up correctly, instead Adams says round them all up and then tinker with the divisor. In that case, we'll have to make the divisor larger to make all of those fair shares smaller so that when we add them all up, we don't get any extra seats that we don't have. Webster's method, same basic idea, says no, just always round to the nearest whole number. And in fact, maybe that'll just work out, right? Maybe you won't have to change the divisor at all. Maybe when you round every fair share to the nearest whole number, you'll just get the number of seats that you want. If you got too many seats, then you make the divisor larger to make the number smaller. If you got not enough seats, if you have leftover seats, you make the divisor larger to make the fair share smaller. So you just sort of tinker with it as needed based on how the original standard divisor works out. But even these alternate methods, Adams's method and Webster's method, can cause the quota rule violations that we saw with Jefferson's method. The method that's currently used for the U.S. House is a little bit more complicated, but it's basically based on these same ideas. It's called the HuntingtonHill Method. But it was actually proved mathematically in 1980 that it's impossible to find an apportionment system that both avoids the paradoxes that we talked about in the previous lecture and also doesn't violate the quota rule. So we're kind of stuck. We have to either have those weird paradoxes or we have to have a rule that may sometimes violate the quota rule. So that's the story on apportionment. We're going to talk about a couple other things in this unit, specifically weighted voting systems, that will start in the next chapter. See you then.